A-Level Mechanics Frameworks. When designing a structure, such as a bridge, a building, a vehicle, an aeroplane, or even a bicycle, it's important to make it as strong and light as possible. To do this, we often design it around a framework. If we have a tube or rod, it can take much greater forces that are longitudinal, that is compression or tension, rather than transversal, that is bending. If you look at the diagrams, we've got two tubes. The first one is under a bending force, and the second one is under compression. The second tube will be able to support a much greater load than the first tube. So, when designing a structure to be as strong as possible, it's best to design it so that its components are, as far as possible, under compression or tension with minimal amounts of bending forces. Now, this can be seen in many different types of structures. For example, if we look at bridges need to be as light and strong as possible, and this can be done in different ways. A very common method is the suspension bridge. A suspension bridge consists of tall columns connected to cables. The columns only take compression forces, and the cables only take tension forces. The roadway itself is supported all along its length by lighter cables, so there's very little bending moment between these cables. A trestle bridge is made of wood or steel beams connected into a framework of triangular shapes. Each beam is then either in tension or compression. Now we define a framework as a rigid structure made of light rods that are smoothly joined together at the ends only. Any loads on the structure can only be at the jointed ends of the rods. If the rods had significant mass, then there would be forces acting along the rod due to their weight. So they must be light, that is, have insignificant weight. Let's have a look at an example. Example 1. A framework consists of 3 light rods hinged at A, B and C, with the angle ABC equal to 60 degrees and the angle ACB equal to 30 degrees. A weight of 20 newtons is attached at A, B and C rest on the ground. Find the normal reactions at the ground and the tension or compression in each rod. To solve this, we can mark the normal reactions at B and C as P and Q. We then need to mark the compression or tension in each rod. The forces at the end of each rod will be equal and opposite. In each rod, the arrows are drawn in the direction the force acts on the hinge. So the arrows push outwards in compression and pull inwards in tension. For each rod, we need to estimate whether it's in compression or tension. Probably AB is in compression. We can call the compression R. Probably AC is also in compression. We can call the compression S. And BC is probably in tension. We can call the tension T. If we guess wrong, it'll become clear when we do the calculations. To solve the question, we can consider the external forces acting on the whole body, a part of the body, or an individual joint or rod. We can resolve or take moments. We have many options to choose from, but if we select wisely, we may be able to derive simpler equations. It's very easy to get a lot of equations, each involving several letters. However, to solve it quickly, it's better if we can find equations that involve only one, or at most 2, different unknown letters. To begin with, we could take moments about B for the whole body. In this case, R, S and T are internal forces, so we can ignore them. The only external forces acting about B are Q and the weight 20 newtons. So we have, when we take moments about B, anti-clockwise we have Q times BC, and clockwise we have the weight 20 newtons times the perpendicular distance of the weight from B. That is 20 newtons times BA cos 60. But BA is equal to BC cos 60, so we have Q times BC equals 20 times BC cos squared 60. And we can cancel the BC on each side to get Q equals 20 times cos squared 60, which is 0.25. And so Q is equal to 5. Now, if we resolve vertically on the whole body, we get P plus Q equals 20, but Q equals 5. So that gives P is equal to 15. If we resolve vertically on the hinge at C, we have the component of the compression, S, acting downwards, that is S cos 60, which is equal to Q. Now cos of 60 is a half, so 0.5 times S equals 5, S equals 10. Now if we resolve vertically on B, acting down we have the component of R, which is R cos 30, equals P. Now the cosine of 30 is root 3 over 2, so root 3 over 2 times R is 15, which means R is 30 over root 3. We can rationalise the denominator by multiplying top and bottom by root 3. That gives us 30 root 3 over 3, or R is equal to 10 root 3. Then resolving horizontally on C, we have T equals the horizontal component of S, which is S cos 30, and so T is equal to 10 times root 3 over 2, so T is equal to 5 root 3. And that gives us our answers: P equals 15 newtons, Q equals 5 newtons, R equals 10 root 3 newtons, S is equal to 10 newtons, and T is equal to 5 root 3 newtons. Example 2. In the diagram, we have a framework with points A and B connected to a vertical wall with A 2 meters above B. The rod AC is horizontal and 4 meters long. D is 1 meter above B and 1 meter from the wall. There are rods AD, BD and CD. There is a weight of 100 newtons connected to C. Find the tension and compression in each rod. Well, to solve this, we notice that C is 1 meter vertically above D and 3 meters horizontally away from D. So we see C is 3 meters further from the wall and 1 meter above D. Then, from Pythagoras' theorem, we have DC is equal to the square root of 1 squared plus 3 squared, which is equal to root 10. So we have, if we mark the angle ACD as theta, sine theta is 1 over root 10, and cos theta is 3 over root 10. So we can mark in some angles, which are 45 degrees, and the forces in the rods. Let's suppose that AC is in tension, with a tension T. DC is in compression, with a compression P. AD is in compression, with a force R. And BD is in compression, with a force S. Taking moments about D on the rod DC, we have T times the perpendicular distance 1 meter equals 100 newtons times the perpendicular distance 3 meters. So that gives us T equals 300. And if we resolve vertically at C, we get P cos 90 minus theta, or P sine theta, is equal to 100. Now the sine of theta is 1 over root 10, so we have P times 1 over root 10 is 100, or P equals 100 root 10. Taking moments about A on the triangle ACD, we have only two external forces. They are S and the weight 100 newtons. So S times AD equals 100 times AC. Now from Pythagoras' theorem we get AD is the square root of 1 squared plus 1 squared, which is the square root of 2. And so we have S times root 2 equals 100 times AC, which is 4. That gives us S is equal to 400 over root 2, and we can rationalise the denominator by multiplying top and bottom by root 2. So that gives us 400 times root 2 over 2, or S is equal to 200 root 2. Now resolving horizontally on D, we have R cos 45 plus S cos 45 equals P cos theta. Now the cosine of 45 is 1 over root 2, and the cosine of theta is 3 over root 10. So we have R times 1 over root 2 plus S times 1 over root 2 equals P times 3 over root 10. Now if we multiply all the way through by root 2 and change P into 100 root 10, we get R plus S is equal to root 2 times 100 root 10 times 3 over root 10. And that simplifies to R plus 200 root 2 equals 300 root 2, or R is equal to 100 root 2. So we have as our solution T is 300 newtons, P is 100 root 10 newtons, R is 100 root 2 newtons, and S is 200 root 2 newtons. Example 3. The diagram shows a framework supported on two blocks at A and B. BD and ACE are horizontal. The angles are marked in the diagram. There is a mass of weight 24 newtons at D. In part A, we're asked to find the normal reactions P and Q. Now to solve this, we can take moments on the whole frame about A. There are two forces that are trying to turn the frame about A, that is the weight at D and the normal reaction at E. Now the weight is a horizontal distance of 3 from A, and Q is a horizontal distance of 4 from A. So we have Q times 4 equals 24 times 3, which means Q is equal to 18. Now, if we resolve vertically on the whole frame, we have P plus Q equals 24, but Q is 18, so P plus 18 is equal to 24, or P is equal to 6. So we have P is equal to 6 newtons, and Q is equal to 18 newtons. Now in part B, we're asked to find the tension or compression in each of the struts. Well, we can draw in the forces in DE, and we can call them S. We can also draw in the forces in CE. We can call those T. We can now resolve vertically on E. The vertical component of S is S cos 45, and that's equal to Q. So S times 1 over root 2 is equal to 18, which gives us S is equal to 18 root 2. If we resolve perpendicularly to DE on E, we get T cosine 45 equals Q cosine 45, which means T is equal to Q, or T is equal to 18 newtons. Now we can mark in the forces on CD as compression, and we can label them U. We can mark in the forces on BD as compression, and label them R. If we resolve along DE on D, we have down R cos 45 plus 24 cos 45, and up we've got S. So R plus 24 times the cosine of 45, which is 1 over root 2, equals 18 root 2. And if we multiply both sides by root 2, we get R plus 24 equals 36, which means R is equal to 12 newtons. Now if we resolve along CD on D, we get, going up, R cos 45 plus U equals, coming down, 24 cos 45. So that gives us U is equal to 24 cos 45 minus R cos 45, or 24 minus R times cos 45. So U is equal to 12 times 1 over root 2, and we can rationalise the denominator by multiplying top and bottom by root 2, so we get 12 times root 2 over root 2 times root 2, which is 12 root 2 over 2, and that gives us U is equal to 6 root 2 newtons. We can now mark in the forces along BC. We'll assume their tension and label them L, and we can draw in the forces along AB, which I'll assume are compression and label them M. We can now resolve along CB on B, and that gives us L equals R cos 45, which means L is equal to 12 times 1 over root 2, and we can rationalise the denominator by multiplying by root 2 over root 2, which gives us 12 root 2 over 2, so L is equal to 6 root 2. Resolving perpendicularly on B, we have M cos 45 equals L cos 45, which means M is equal to L, or M is equal to 6 root 2 newtons. Now we can mark in the forces along AC, which will assume a tension, and label them N. Now if we resolve along CA on A, we have N is equal to M cos 45, but M is 6 root 2 and cos 45 is 1 over root 2. So N is equal to 6 root 2 times 1 over root 2, which is equal to 6. So we have N is equal to 6 newtons.